So good morning, everyone. We'll start today's session. As all of you know, on Saturdays we are having the sessions by people who are working in organizations so that they can share their experiences. So in today's session, we'll be having the talk by two people. One is Adithya. Adithya can raise your hand. Everybody knows Adithya, I guess. So he is working as a software engineering specialist in G transportation. And another gentleman is Anush. He is working as software engineer in JP Morgan. You may have seen both these guys roaming around in the college, mainly because they are our alumni who passed through before 2 years, right?
Yes, sir, 2019.
2019 batch. So they are going to present the topics regarding data science, but from a perspective of a language called Julia. Most of you in IS department are already aware of the language Julia. We in IS department are very much uh, proponents of this language for various reasons. So I thought it will be a nice exposure for all of you to see the concepts which you're already studying, to see how those concepts can be implemented in a language like Julia, which is a purely functional language, unlike Python, which most of you are using, which is predominantly an imperative programming language. So who will start among both of you? To whom shall I
Yeah.
pass on the host rights?
Um,
Anush.
Madi, sir, I'll start and Aditya will share the screen.
Who will share the screen? I should make them host.
Yeah, you can make Aditya the host.
Aditya, ready ಏನೋ ನಿನ್ನ ಹೋಸ್ಟ್ ಮಾಡ್ತೀನಿ, you can share your screen.
Sure, sir. Ready.
Okay, Aditya, you can share your screen. ಆ ಕಂಪ್ಯೂಟರ್ ಮುಂದೆ ಒಂದು ಬೇಬಿ ಲೈಟ್ ಅಂತ ಸಿಗುತ್ತೆ, ನಾವು ಫಿಲ್ಮ್ ಅಲ್ಲೆಲ್ಲ ಯೂಸ್ ಮಾಡ್ತೀವಿ, ಹಾಕೊಳ್ಳೋ ಆದಿತ್ಯ ಮುಖನೇ ಕಾಣ. ಆಯ್ತು, ಪರವಾಗಿಲ್ಲ, ವಿಡಿಯೋ ಆಫ್ ಮಾಡ್ಬೋದು, ಪರವಾಗಿಲ್ಲ. ಯು ಕ್ಯಾನ್ ಶೇರ್ ಸ್ಕ್ರೀನ್.
Just one sec.
No problem.
Okay. So let me know when you guys are able to see my screen.
ಕಾಣ್ತಾ ಇದೆ, ಕಾಣ್ತಾ ಇದೆ. ಸ್ವಲ್ಪ ಒಂದ್ಸಲ ಜೂಮ್ ಹೊತ್ಬಿಡು.
Okay.
Okay, fine.
Better?
Okay. Yeah, this is better. This is better. Keep it.
Okay. All right, so we'll start. So hi all, thanks for joining. And today we'll just try to do a code walkthrough on some of the data science concepts which we try to implement in Julia. And our environment for today, we are using Colabs. Now Colabs is, most of you would be aware that it's a Google version of Python notebooks. And really the advantages of using that you really don't have to maintain any dependencies or maintain package dependencies on your local system. You can let Google take care of all those things, and even the runtime is on the Google's machine. So it's quite convenient to use it. So, but primarily Google Colab is supported for Python. If you want to run Julia, you'll have to do a small workaround. So I mean, the instructions are there. Probably we can share this notebook later. So the way you can do is like, probably you can download this notebook and re-upload them in your Google Colab account and run the first cell, which is displayed on the screen. And after everything, after it installs Julia, then you're good to go. So that's how you set up the environment. And yeah, so I guess we already ran this, right, Aditya?
Yeah, so one thing which all of you should know is Julia tends to do this thing where in the beginning of using a package or even installing a package takes a lot of time. But you should not be demotivated by that, because at the first pass, what it does is once the entire module is loaded, it caches everything like this. And once that is done, every time you run again, when the your runtime is connected to the system, it is faster. So initially, if you guys want to give it a shot, and later after the session you want to run this notebook, you might feel there's a lag and like this. It takes a lot of time, maybe like at least 5 minutes. But please do give it a try. Yeah, we good to go, Anush.
Yeah. All right. So I'll start with supervised learning, and primarily I'll start with regression. Yeah. Okay. Before we start, I think uh, the way you install packages on Julia is there is a like in Python you have pip. Julia has its own package manager called pkg, and whatever you want to specify, you speak instead of import, you can say using package and then package.add whichever package you want, and you can install it and it'll have things ready for you. So so today for supervised machine learning, I'll be covering two libraries which I felt was very good. One is Flux and the other one is MLJ. Now what I'll start over with Flux and I'll get to MLJ later. Now what Flux is, the way I would like to call it, it's a library which helps you calculate gradients, and it is very similar to PyTorch and TensorFlow, if most of you are familiar with that. Now, the advantage of having such a library is that if you have gradients, then you can pretty much solve any deep learning problem. As you can scroll down a bit. Right. Yeah, I can stop. So the idea behind deep learning would be that, like, let's say you have a function in which you need to fit a data to. So what you do is, like, you pass the data to your function and then you get an output. You calculate the loss for that output. Now, once you have the loss, then you need to calculate your gradients of all your parameters in the function with respect to the loss. Now, once you have that, all you need to do is you need to update your parameters based on the gradient. That's all there is to deep learning. And Flux is that library which helps you calculate gradients, and it makes you easier and makes it really easy to implement any function of your choice, and you can play around with it a lot. So so for linear regression, I think let's start. We can create a synthetic data set. I think you can scroll down a bit. Yeah, so we can create a synthetic data set, let's say for n equals 100, and then you can, let's say we initialize x with a two-dimensional array of ones. Now, once that is done, now what I'm doing here is, like, for the first column of your array x, I'm trying to initialize it randomly with a uniform distribution. Now, a lot of things here are quite similar to Python. Now, if you were to do it in NumPy, you would do NumPy.ones. And then if you were to do it, if you were to initialize in Python, you would do numpy.randomn, or even you can pass a distribution here. Now in Julia, you have a distributions package, which if you give it a parameters, like here it's distribution.uniform, and you're telling, give me a give me n numbers from a uniform distribution of range -1 to 1, and then we assign it to the first column of your x. Now that's how I'm creating my x over here. And then once we have x, we'll need to take y. And now let's say if our hypothetical function, which a true value function, is f of x equals 3x plus 2, we'll create target variable y accordingly. Now, if we define your weights as a, which is 3 and 2, then your y will be x times a, that will be your y. But to add a little bit of noise to it, I've also included a random function over there. So now this prepares your data. which is X and Y. Now we can also go ahead and visualize this. I think you can scroll down a bit. Yeah, and you can execute it along the way. Should be working. Yeah, so in Julia, you also have the plots function, plots library, which is very similar to matplotlib. And you see GR over there, that just determines the backend library which you're using. Julia has a lot of libraries which you can use. GR is one such. Now, once you define that in your plot function, you specify the first parameter takes one variable, the second parameter takes another variable, the third parameter sort of tells you which type of plot you're using, which is if you want a scatter plot or a line plot or anything like that. Now we see it's behaving a linear pattern over here. Now we can get to try to learn a function. Now, I mean, we already know that it's 3 and 2, but let's try to learn those variables. Yeah, you can scroll down a bit. So as I said before, in a deep learning perspective, it's about like once you have a function you're trying to fit into a data, you try to take a loss, and then only with respect to that loss you take your gradients, and that's how you try to decrease your loss. So first, for linear regression, we'll have to define a loss function. The most popular one would be a mean squared loss. Now, what mean squared loss is, like, let's say you have your true variable y, and then you have your predicted variable y hat. You subtract, you subtract those two, and then you raise it to the power 2. And this is your mean squared loss. Now, one thing what you can notice there is the dot operator over there. I heard sir talking about people are familiar with Julia over here. So uh, I would, I'm assuming most of you know that, but for people who are not familiar, the dot operator over there, what do I mean by that? We see dot minus and dot exponential 2. So the dot is an element-wise operator. So let's say you have two arrays, the first array being 1 and 2, the second array being 3, 4. Now, if you do dot minus between those two arrays, it gives you an element-wise subtraction. It will be the value what you get is 1 minus 3 and 2 minus 4. So your new array will be -2 and -2. So when you do dot minus, it always is an element-wise operation. So once you define your loss function, and Julia, you define your functions by functions and give your name, the input parameters it takes, and you always end it with an end directive. So once you define that function, we can go ahead and initialize our weights again, but this time we'll make it as random because that is something which we need to learn. So once you define those weights, and then you can calculate your y hat, and then you can calculate your loss just to see how it is behaving with random weights. Yeah. So now the loss is around 656, which is pretty bad. We'll need to improve it. Again, we can visualize that again. And this time in your plot function, if you notice, I also have an exclamation mark. So what that does, it's updating your previous plot object. So in Julia, when you give an exclamation mark, you're directly performing on the objects there. And it's quite analogous to pass by reference. So that is the thing. So on the previous plot, we are trying to do another scatter plot of y. So in this case, it is y hat, and what it is showing it is it's not behaving pretty well right now. Yeah, you can scroll down. Yeah. So now we'll get to the core of Flux and why is it so powerful, and we'll see how that helps us do linear regression. Now, whenever we do anything in deep learning, there are really 3 to 4 important things which you need to think. One is about defining your model. In our case, it is a very simple model, which is just in the form of y is equal to mx plus c. That will be our function. You can see the way I have defined it as y hat is equals x into a. And next is that once you have your model, you need to take your loss. Loss is something which we defined as mean squared loss in the above cell. Now, once you have your loss, you need to tell Flux like, hey, these are my parameters, which is A, and then you need to fetch me the partial derivatives of all of these parameters with respect to loss. That is exactly what the gradient function is in Flux. If you see, the gradient function takes a callback, which is your mean squared loss, and I'm passing x into A, which is my model, and my y, which is my true target. And then I'm also registering my parameters with Flux. The way I do it is flux.params of A. Now that is what telling Flux, hey, however these parameters are scaled, you need to take the gradients of them. Now, once you get those gradients, once you get those gradients, it kind of tells you the direction in which you need to move each parameter, so that ultimately you aim to minimize your total loss. So now you can update your gradients by a small value. Again, notice the dot minus operation over there. Uh, it's very convenient to do that. You don't have to loop through all the parameters over there. Now we can update our weights, which is A, and you can do dot minus of learning rate times gradients of A. So what your learning rate is here is telling you is that how fast you need to update your weights. So what your gradients, let's say your gradient is 2, and if your learning rate is 0.1, so your update parameter would be, yeah, of course, 0.1 into 2. So if your learning rate is too high, you're telling the machine to learn the function faster. And if your learning rate is too slow, you're just telling it to, hey, take it slowly. We'll do a lot of steps, but we'll try to learn it very slowly. And that's the concept about learning rate. And that is, learning rate is something what we really, it's a hyperparameter, and there is no correct value to it, but it's something what most practitioners play around to get it trained well. So I have specified a return statement over here, but in Julia, you really don't have to. Like in Python, if most of you are familiar with Python, if you want to return something, you do specify return, else it's null. But in Julia, the last statement which gets executed will always get returned. So this is our update function. So the key takeaways here would be, you define your model, uh, you define your loss function, you take the partial derivative of all your parameters with respect to the loss, and then you update those parameters. And when you repeat the step for, let's say, n steps, and hopefully your loss will become less. So Adithya, you can just execute that function. Okay. And now let's say our learning rate, we define it as 0.01, and I start with my weights of -1 and 1, and I'm running it for 100 epochs. And for every epoch, I do an update. Epoch is basically a fancy term for telling how many times has your update function seen the data. So in our case, I'm putting it for 100 times. And you can see the loss is gradually going down from 171 to 7, which it's probably doing a little better than what it did before. You can go down. So just to verify that, you can like try and visualize it again. Um, Again, first, you create a scatter plot with just X and Y, and then you modify the same object by giving your old X and the new Y. So we can see that it's converged, and it's doing much better than what it was randomly doing. So, and yeah, once it does, it's also important to see your weights if they are close enough to what we had created the synthetic data to. I think I can scroll down. Yeah, and if you execute that, you see it's pretty close, 2.9 and 2.4. It's close to what we had done. We had created the data set to, but of course, there will be some changes because we had also used a random number while creating targets. So that is mostly about linear regression when you try to do it in an iterative fashion. So really things to remember here are, like, you need to define one function which you need to fit into the data. Once you have that function, define your loss. After you define your loss, get your partial derivatives of all the parameters in your function with respect to the loss, which the gradient function in Flux gives you that ability to. Once you have that gradient function, update your weights um, with respect to a learning rate, and you repeat this for like n steps, and eventually, hopefully, your loss will decrease along the way. So that is for linear regression. The same steps, you can go ahead and do it for polynomial regression. Um, Again, like I just created a different function over here. You can see f of x is now 2x plus 4x squared plus 1. I'm creating y accordingly. Now, again, this is a synthetic data set. Adithya can go through, run those cells. And now, again, we can plot that. Yeah. And now only this time, instead of earlier where we tried to fit a linear function, which was in the form of x plus c or mx plus c, we'll try to fit in a polynomial curve here. Since this is regression again, your loss function remains the same, which is your mean squared loss. And not sure why I have that. You can go down. Yeah, so once you define your synthetic data, we can check what is our mean squared loss. And let's say A is defined to be at random. It is nowhere close to what parameters you use to create your data set. Yeah, we can also visualize it again. Now, I'm defining another function called g. G is pretty much telling the first parameter in a times variable plus the second parameter times variable square plus your constant, which is most of the times referred to as bias term. And so now the first plot function is plotting a scatter plot of x and y's. And now then when you give a plot and an exclamation mark, you give your function and then you give a range for that function. It gives you a line plot on top of the older plot. So that's that. And your update function remains the same, which is x times a. And again, you can just pass it over and for 100 epochs, and your loss will eventually go down. And hopefully your A's is similar to. Yeah, and yes, it's okay-ish. It's not as good. Probably we can like redo it to get a better curve. No, that's okay. So another thing what we can keep in mind is the concept of underfitting and overfitting. So what underfitting is like your function is too simple for the given nature of data. So let's say your data follows a uh, polynomial way of degree 2, but then you try to fit a linear curve over there. It'll fit well, but its predictability is not that great. So that in simple terms is underfitting. What overfitting is that your function, what you try to fit into your data, is way too complex for the data. Let's say if you have defined your data as to a polynomial degree 2, and then like you're trying to fit a polynomial function of degree 4. So that's overfitting your data. Now, overfitting is probably bad because it'll just fit your data properly, and anything which goes beyond and it's not in your data set, it will not try to predict properly. So that's one reason. We can just plot those. I mean, if you go down, we can plot and see why that is bad. So the concept remains the same. Those functions are pretty much the same. There's no updates here. So this is underfitting. So it is really not describing your data well. Now, when you try to overfit, which is yeah. Now, if you see that it's not a smooth curve, there are sharp turns, and that is something which we should generally avoid. one way to solve overfitting is, I don't have a code example here, is by having good amount of regularization. So regularization is that which can help you prevent your weights from being blown up. Like, let's say, even if you have given a polynomial equation of degree 4, and then you are trying to fit that curve here, what regression can help you do, what regularization can help you do is that it'll try to learn it in such a way that the parameter of the the equation, let's say x raised to 4, is very close to 0, so that it's as good as not having it at all. So, and then eventually you'll get a smoother curve. So this is about regression. You can go ahead and probably do the same thing for classification. There is not much difference there. So in classification, the only thing you'll probably need to change is change your loss function. You'll probably have a logistic loss over there. And then, of course, while creating your synthetic data set, you can just create a random equation of your choice and define a threshold of your choice. And if it's greater than the threshold, mark y as 1, and less than threshold, you can mark y as 0. You can create the data set, you can update your loss function, and then, of course, you can calculate your gradients based on the update function defined above. You guys can try it out if interested. So that's how you extend to classification. Any questions till now? Anyone wants?
Aditya or Anush, anybody can just explain the difference ಅದು ಹೇಳಿದ್ದೀರಾ the way Python ಅಲ್ಲಿ ಮತ್ತೆ ಜೂಲಿಯಾದಲ್ಲಿ differences and all you have observed. But one of the USPs that we keep trying to impress upon people about Julia is that how computationally it is much better than Python. So when you are
Yes.
working in Julia, have you come across that and can you share something about that? Of course,
Sir, yeah, we have some examples. I thought like we'll keep it a little to the later end, but if you want, we can give a few now itself. Anush, like if you have any
if you're covering it
coordinates.
later, then it is fine. Then it's fine. I wanted that thing to come out very clearly so that people can understand the
Yeah,
differences in
so
performance of both these platforms.
yeah, we have a few examples where we are comparing certain clustering algorithms with when you use scikit-learn and when you use the Julia packages like clustering jail.
Yeah.
And we are going to stress upon that fact, because when we were learning Julia and writing this code, we actually appreciated that fact more, and we actually understood how important and beneficial it can be while teaching people machine learning, but at the same time not missing out on the fact of every step or every equation which acts like a checkpoint when you're actually computing is also covered in Julia, and you don't get to skip on that.
Yeah.
So
Okay.
we will cover that.
Sure, sure, sure.
And just to add on to that,
Anush, you can carry on. Yeah.
Yeah. Anush, keep an eye on the clock also.
Okay.
ಈಗ ಅರ್ಧ ಗಂಟೆ
Okay.
ಆಗೋಯ್ತು ಇನ್ 30 minutes ಇದೆ 11 o'clock I should close the session, that's why.
Okay. Okay. I'll try to be a bit faster. Another library which we find it very interesting was MLJ. So during the development of Julia, what happened was different subcommunities started developing their algorithms on their own, and really they had their own implementations. So what MLJ does is, it's a neat way of combining of wrap what MLJ basically does is it wraps all those libraries and gives you a common framework to run all your algorithms. So it's pretty similar to scikit-learn. So, and yeah, the framework is like you can use whichever backend you want, but then the way you train your models will be quite similar. So you can scroll a bit up. So just for demonstration purposes, we can use an R dataset package. Let's say we are using a long read dataset. This dataset is basically telling you, giving you the number of people employed based on certain factors. So that's most about data. You can look up the data. So one interesting thing about MLJ is that they try to define a schema for any data set you have. Now, Alti, can you run that cell or scroll down? Yeah, and in your schema, you can notice for every feature you have, there are two types. One is just a type, and then there is a scientific type. Now, why that is important is because the way you store in your machine can be many ways. It can be int, or it can be float, or any such things. But the way you interpret it has to be one of the scientific types. Now, continuous or count or float. Now, the key advantage of this is that now let's say if your target variable is being stored as 1, 2, 3, and 4, where if it's a classification problem, you wouldn't want to interpret that as a continuous variable, but rather as a categorical variable. So MLJ gives you that functionality to help you determine how you should interpret each feature. Now, why is that important is because MLJ also gives you a recommendation. So which I have examples later. Probably we can go through that. Once you have defined your data set, we can separate the data set into X and Y pairs. The way you do that is unpacked. Now, data here is data frame, and it's quite similar to pandas in Python. Data frames.jl is something what you have in Julia, and all the functions in pandas, you'll find it here as well. So, yep, you can unpack that. Yes, and so as I told, there are a lot of different implementations of machine learning algorithms, and MLJ does a good job of combining them and giving you a common interface to execute all of them. We had already added this, okay. So let's say you want to use a Julia package called as MLJ linear models. All we do is we load it. Now, also you see that there is an at load over there. Now what at load is, it's a macro. What that does is it's getting the source code into the MLJ system. Now, since these libraries are defined outside MLJ, you need to get it inside MLJ for it to use it. Now, for a linear model, we can use linear regression, lasso regression, or whatever you choose. Now, in your linear regression, what that is, it's a simple struct. It's quite similar to a class, and that gives you a hyperparameter in which you can use to calculate, to fit your model. Now, once you choose which model or a struct you want to use, then you need to combine your model and data into a single thing called machine. I think that was in the upper cell. Um, yes, one machine is just wrapping your model and data. And then once you have your machine ready, what we do is we use the fit function to fit it. And before fitting the function, of course, we'll split the data into train and test. The way I have done it is using stable RNG. Stable RNG is nothing but a random number generator, and the seed value is 566. The seed values are important for reproducibility perspectives. And once we do that, you can use your fit function on the machine you defined and on what rows you want to fit it to. And once that is fit, and you can use the predict function on the machine itself to just get a predictions of whatever rows you have. And then if you want to interpret what's going on, you can also use the fitted params function to see what are the values of each thing it has taken. So you can also evaluate using k-fold cross validation. So CV is just cross validation, and you're doing a threefold validation over here. So, and for your measure, you can use L2. So this is just all you need to do in MLJ. You need to define your backend, which algorithm you want to, you load it, you define it in a machine, and all you do is fit and then predict. So I think we have one example below where, can you scroll down? Yeah, we can do similar things for decision trees. I think what the linear regression implementation there in MLJ was not an iterative approach. It was more like a matrix decomposition approach. So that was that. And yeah, I think Aditya, you can scroll down a bit to the places where we have imported a data set. No, you can scroll down. Yeah, and pretty much all the functions you have on pandas, you have it in Julia as well, such as describe and head. So yeah, yeah, you can stop here. So Can you scroll up a bit? Yeah. Now, why that schema was important is because like MLJ itself tells you which algorithm you can use for your data set. Now, if provided you have defined your schema properly, you can use a matching of your input and target, and it gives you a models function. It tells you which package name, which algorithm you want to use, and which is suited for that data. So it really does a nice job of that, and that's why define your scientific types was really important. If you, yeah, you can go down. Now, yeah. Yes. Instead of using our data set, if you have a CSV file, you can use a CSV library to load it into a data frame as well. So yeah, you can execute that. Now, yeah, let's quickly check what schema it is. Now, let's say we want the type to be not a count, and which is our target. We want it to be considered as an ordered factor. An ordered factor is pretty similar to categorical array. Now, the function which is used to change the scientific type is called as coerce. Once you change that, your schema is changed into an ordered factor, and now you can ask MLJ which algorithm is best suited for this data. Yeah, you can go down to matching. Yeah. In matching now, you have a list of algorithms now which is best suited for this data, and you can choose anything from this. You all you need to do is install that package, load it using the load macro, and all you do is create a machine which is a wrap of your model and your data. Once you have that wrapped, you pretty much do fit and predict, and that is very interesting thing about MLJ. It really simplifies a lot. Instead of you searching for all the different implementations in Julia with different packages and stuff, so you have everything in one place, and it has a common framework to do things. So yeah, if you go below, you will find implementations for KNN and I think naive Bayes, which I'll probably skip. You guys can, if you guys are interested, you can go through the code. So these were two things on supervised learning. I think Adithya will talk about unsupervised ML.
Okay, yeah. So thank you, Anush. And so guys, I know this is a lot of information to take in. So we are trying to just give you a brief understanding of how you can use Julia and learn machine learning. The main purpose of Julia was to understand machine learning in such a way that it shouldn't be too much of information, but at the same time, you're not missing out on the important points. Normally, when it comes to machine learning, there's a lot of equations and basic steps, and there are always where you can go to a finer granularity where you go and study every algorithm in depth, and then there are sometimes where you just want to know the key steps, and you can that'll be very good for a basic beginner learner, and also that will be your foundation when you're moving to the advanced stages. um, so in unsupervised machine learning, I'll be covering a topic called dimensionality reduction and also some of the clustering algorithms. So when we come to dimensionality reduction, there are many methods. You can do some missing value replacements, missing value ratios, and then there are certain important methods. And one of them, which were found out to be very effective, was the principal component analysis. um, so now if you see in scikit-learn, you'll have this. You have something like this where you do an incremental PCA and like simple steps. And even in Julia, you have something in similar. So first thing is like I'm using Iris dataset, which I loaded from our datasets package. And so first step is the basics, like how Anush covered it. So I'm just taking, I'm using the dataset package to get the data frame. Once I've loaded my data frame, I'm using a more what you can say is like a naive approach. I'm just splitting the arrays in half, splitting the data frame into half and converting them into arrays. So I'm creating a train and test with just manual array manipulation, nothing extra. So yeah, so the library what we'll be using over here is called the Multivariate Stats JL. So this is Multivariate Stats. So in Multivariate Stats, you have many detailed information of what each properties do, and also you have very simple methods like the way you use in scikit-learn, and at the same time even you get like a mathematical explanation over here of exactly what happens when you're converting each when you convert an entire huge data set of, I don't know, like think of like 50 or 150 features, and you don't want all of them because that'll be a huge data set and occupies a lot of memory and requires huge computation powers. But in fact you want to just minimalize it and come up with uh, a small distinct uh, value, but at the same time you are also not losing a lot of data. So you'll be transforming like a high dimensional data to a low dimensional. I know that most of you know that. And so when we come here, uh, in multivariate stats we go in three steps. The first thing is the way you calculate the PCA model. So when you're calculating the PCA model, you will be given options like you can use either an uh, covariance matrix method, or you can use even a singular value decomposition method. So it's bare right now. Like there are default method is like if your principal components are less than the total size of your maximum dimensions present in the feature data set, it uses the covariance matrix method. But if you feel like you might get a better result if you use the SVD method, you can use that as well. So for now I'm stuck to the defaults, and I'm using the transform the basic. What I'm doing is like there are four features in the iris data set, as you all know: the petal width, uh, the petal length, and the sepal width and the sepal uh, length. So what I'll be doing is, this is not like a great example. I have, but for the beginner's sake, so I'm using a data set which has around four features, and I just want three out of them so that I can represent them in a 3D dimensional space. So I've taken that, and first thing what to do is fit. So once you fit, the PCA model is trained, and you will be training one PCA matrix which will have three dimensions. And then the next thing to do is, once you've trained it on your training data set, it's time to test whether your PCA model is at least able to get a good prediction. So the next thing what you do is you try to apply this PCA model on the testing data set. Now, once you get the testing data set, you will be actually trying to compare with the model and trying to see when you'll recreate the observations, the testing observations based on this value. So this will be more like comparing um, the values what you predicted and the value on the values what you tested it. Are they almost same? So that's when you use reconstruct. And now one of the most, like when you're learning data science, visualization of data is very important, because not when you're think you're like going and explaining a new data science, you use some, you've taken some company data and you're projecting them some idea of this is how it's going to be. And if you always want to attract more audience and grasp their attention, visualization of data is very important. So Julia has multiple libraries, just like Anush said. So I'm just using Plotly over here. And if you notice in supervised learning, we were using GR. So this is one of the backend interacting graphing models. So on running this code cell, we will get an amazing 3D plot, and it's so fun, and it makes you like like makes you think like, okay, so this is something I just did with a simple data set like Iris. Think what I can do with some data set which you get from real time, and do work on it. And then when you start explaining things like, okay, so if you see, like, these are the three principal component analysis. So y1 is like the first principal component analysis, y2 is your second principal component, y3 is your third. So the y1 data set, it explains, has the most variance, and it has like it explains the maximum variance in the data set and gives you a lot of information. And the y2 is having something less of a variance, and it is actually uncorrelated to the y1. And what are those features over here? So important stuff like that. So now let's move to a way where we use a real life data set. So the one what I'm using is called the wine data set. So here what we do is you have different types of wine based on around, you have around 13 to 14 features in it. Now that's a lot of features. So you don't need 13 to 14 features. You just need the three best out of them. You need to just find three features and just represent it easily so that you are able to predict. So that's what we have done over here. And here we go. So as you can see, like there's not there is not like huge uncorrelated space, or like there's not like a huge gap, since there are a lot of close relationship is present. But still you are able to visualize them, and you're able to understand like which component. So this is all y1. So first principal component is all in blue, and then you have the y2, and then you have the y3. Similar things like that. And as you can see, like we have used the same way how Anush explained the scatter plot. The first thing what I'm doing is I'm plotting the principal component analysis of the first principal component, and then I'm appending it with the second principal component, and then I'm appending it with the third using the exclamatory mark. Very useful operator. It helps you to visualize in great detail. Um, in Julia collabs, you have to keep in mind that there are little restrictions when it comes to interactive plotting. But if you have it in your base system, you can do much more. You can have a slider, and you can also you can replace the axes with other features. So right now we just have PC1, PC2, PC3. If you want to do it with 4, 5, and 6, you can replace it with that, or check what is the correlate, how would the clustering look if you have PC1, PC2, and PC4 rather than PC3 and stuff like that. So now coming to an important part. So this is where it gets interesting. So in Julia, you can do it in both ways. Like you can have matrix. You can use libraries which are very simple and just takes like 3 to 4 lines of code, very beginner level, and come up with great outputs. And you can start learning on a smaller level. And then at the same time, when you want to get in depth, and then you want to start learning, like how would you like, for example, like if you I think we'll see a detailed explanation in DB scan. So let me just go through this one important topic, which is normalization. Now, normalization is very important in deep learning, because if you have a data set where when you describe it, you have uh, you have a column which has all the values between 0 and 1, and then you have another feature column which has values from 0 to 10,000. Now when you are computing a matrix, if you have one particular column with values in the order of 10 power 4 or 10 power 5, it will obviously make the matrix and the gradients what you calculate on it explode, and the computation goes on increasing exponentially, and it becomes very difficult. So the best thing to do is always scale your data set before doing anything else. When you're pre-processing, please scale your data set, normalize it using So here, if you see, this is what your output will be if you don't normalize. It's the same code, and you'll see that they're like tightly compact, and like the scale, if you see, is like huge. It's in the orders of -60, -40, and then there's like 10, 5, -5 to 10, and then this is a smaller axis where it's just from -5 to 5. So they're not equal. So you can, if you so here what I'm using is called a library called StatSpace. Now, if you normalize it, I'm using just the basic unit range transformation, and with using unit range transformation, I have normalized it to a simpler scale of, I think, between 0 to -1 to 1. If you can see, before it was all in the orders of tens and units. If you can see, it's like this one 5 to 10, this one 60 to 20, and this is from 5 to -5 to +5. But here it's all in between 0 to 1. That's what unit range transformation does to your data set. It keeps everything in 0 to 1, helps calculation as well as handling the data set more easier, and makes the data representation more meaningful. So if you can see now, you can see the clear distinction between each principal component analysis. Like they're also not tightly compact, and so that you can't make much difference out of it, but now you can see them more clearly, and even the representation becomes easier as you improve the scale. So now coming to thinking about a simple DB scan algorithm when you learn from the basics. So if you use scikit-learn and try to do a DB scan code, um, yes, bring that up. Just give me a second. I'm just trying to find a scikit-learn DB scan. This is something I found on the net, just like default. So here, if you can see, so if you do a DB scan clustering on a random data set using the scikit-learn cluster DB scan module, so we got a randomly generated array, and then they're just directly going DB scan with the epsilon equal to 3 and the minimum samples equal to 2. So you can, the max you can do is just come here and just see what's like what is epsilon. So it says maximum distance between two samples. That's it. Now, if you are someone who's new to who's new to machine learning or data science, and you want to know what is this EPS value and what is it, why are they calculating this maximum distance between two samples, or what is the need to calculate between the two samples, and then again when you come to see what is this minimum samples and what do you want to know about that, that's when Julia plays in a better way. In Julia, they take it like one step, like they break the entire process into two steps rather than make it one simple call of functions. What they do is they require you, even here you calculate the radius, which is the EPS value, but at the same time, you have to calculate something called as the distance matrix. So the distance matrix, what it does is it is used for calculating the distance between one point and the other. So here we are using a basic Euclidean distance to calculate the distance matrix. So this distance matrix, now you'll be clear like, okay, so before computing, this is one of the pre-processing steps what is required for the DB scan. So first step would be to calculate the distance matrix between each of these points for the entire matrix. What you have over here, you calculate this distance matrix where you do same thing where you do x1 minus x2 the whole square under root plus y1 minus y2 the whole square. Then you calculate the distance matrix. So here we have something called as the distances library in Julia, and we use that. So in Julia, you have to keep one thing in mind is that the matrix always is calculated with columns comma rows, then rows comma columns. So most of the time it's always the transpose, and that's why you need to be careful of what dimensionality you're passing. So if you give the dimensionality access as 1, it is with the columns. If you give it with 2, it's with rows, like that. And now once you get your distance matrix, you pass it, and this is the epsilon value and the minimum samples which I've given in each cluster. So you get your model, and then when you go and plot it against it, so in DB-scan you get you get these members of that function. So you have assignments, you have seeds, you have counts. So all these are just like when you do a k-means clustering, you have centers, you have the variances that you can take those values. So these are the values, and you can plot it with respect to that. So this gives you, the assignments gives you all the cluster indices. So where each cluster points are there, and very easy to later on give some color and distinguish between them. So I have randomly generated uh, three matrices of like certain distances between them. Um, since DB-scan is like mostly used for geospatial data, where you want to plot some kind of heat maps. Like for example, like you want to do something right now with the COVID situation, and you want to do some heat map on based on the number of cases that have been recorded and the population density. If you want to calculate anything with regards to population density, I would recommend to use DB-scan. That's what most of the experts recommend as well. And the same basics goes everywhere. Normalization is key whenever when you're handling real-time data set. You can see a lot of differences when you use. So I've used Iris data set over here, and like if you can see, some of them over here, which are in blue, are not identified as red. If you use k-means, you can see that this section is all green, and this section is all red and blue. So like that. And going up, we have another kind of clustering, which is hierarchical clustering. You have hierarchical, you have agglomerative, you have so many types of clustering. I'm taking up hierarchical clustering over here. In hierarchical clustering, we use something called as dendrograms. So a dendrogram is like you have it starts with one with that neighboring points and distance, and it starts growing as these two converge to become one, and then there is another node. So dendrograms you use to plot. We use something called as hierarchical clustering, which is H plus as a short form for the function. So you have many types of linkage. I'm just using the basic single linkage. Then we are using something. So this is an example using just a random generator. And over here, if you can see this step, you can notice that I'm adding this distance matrix with its transpose. The reason I do that is this is a very important step when you're doing hierarchical clustering, is that your distance matrix should be symmetric. So this step again, if you use a scikit-learn application, is not given. You don't go through this step because it just directly says, "Give me a matrix, I will do this step for you." But if you don't know why you're doing, is there a symmetric matrix involved while doing hierarchical clustering, then you will not be able to sometimes understand the entire concept in depth. So that is where Julia again, like it plays a big role in educating anyone who is new to machine learning, or even if you had used machine learning before in a different language like R or Python. And when you come use Julia, you'll be actually intrigued, because you'll be like, normally I'm just passing a distance matrix and it should work, but it doesn't work. It works only when you know like what you're doing, and like you pass the right steps and you cover each equation step by step. So that is where I would like to appreciate Julia, because it helps you understand a concept which you would have learned it in a different way in the beginning, but then it makes you realize that you are missing some important steps. Because learning machine learning in theory and doing it in practice is a completely different, I can say a different world, but it helps you a lot when you learn to code these algorithms, because in the long run it helps you to when you step into the world of deep learning and you are going through this neural network architectures, it helps you a lot of that. So here if you see in the previous example, I used a single linkage. Here I'm just using average linkage. So yeah, so again I've taken a wholesale customers data set. One thing when you're working in Colab, please do make sure that when you're running the Jupyter notebook, you have uploaded your data set. All these data sets, what you upload is temporary. Every time you close, it gets disappeared. So you have to keep uploading them. If you don't do that, you might get some errors. And the same thing. So first thing, calculate your distance matrix for a real-time data set over here using the Euclidean distance. And then once you've calculated it, it's called a proximity matrix or a distance matrix for the same. So then I calculate a symmetric matrix. Once I have done with the symmetric matrix, I plot a hierarchical clustering dendrogram. So this is how the dendrogram looks. Here is a huge data set, and this is without normalizing. Once you normalize it, it's a little bit more clearer, but like since you have a lot of endpoints in a huge data set, this is how it would look. So yeah, any questions? I'm done with my presentation.
Aditya, the comparison.
Uh, Other said like, so that's what I was explaining. So like,
Yeah, you
so
told.
yeah, it's over. Sir. So what I was suggesting that like in Julia, it's like if you do it, if you do a line, if you do a hierarchical clustering, for example, that's what I explained. If you do a hierarchical clustering on a real-time data set using scikit-learn, the first thing you'll be doing is just get a scikit-learn pre-processing module. You'll pre-process it. If you want to normalize it, you'll use a scikit-learn normalization. That step is here. But then directly you will go and plot the dendrogram using the scikit-learn. In Julia, you go with two more steps, which is first thing is always calculating a distance matrix when you're handling clustering algorithms. Once you calculate the distance matrix, you calculate whether it's a symmetric the distance matrix for this particular input for this particular algorithm, and then only you will go ahead in plotting. Otherwise, it would never it wouldn't take the data set. You can't directly pass x over here unless until you calculate the distance matrix. Now these two steps are very important and you learn it only in theory, but in practice when you're using scikit-learn you never get to use it. So if you would have, if you are someone who started just directly coding Python, coding data science algorithms using Python based on tutorials, you'd never go through these steps. And that is the beauty of Julia. Like it helps you understand those integrate small steps, which you feel, which most of them feel unnecessary but very important. Because like you can do so many. These acts as hyperparameters as well. You can do some small tweaks and get some better outputs as well. So that is the key difference.
Yeah, thank you, Aditya. And I think you'll be sharing the it Olga,
Yeah,
the
yes,
page.
sir. We have created this. So this has both, and this is more cleaner. And I think we'll
Yeah,
just share a Google Colab notebook, and
share
we
with.
will, yeah, we will attach these files, sir. So I've
Sure, sure.
explained that they have to
Yeah.
upload it every time.
Yes, yes, yes.
That's the only
So you
hassle.
send it to me, so I'll share it to the class. Thank
Yes.
you very much, both of you, for the presentation. And if there is any questions, I will definitely pass it on to both of you because now I have to close the session.
Sure, sir.
I have
Sure.
exceeded the time. If anybody has a question, you can please send it to me, or what you can do is once the code is shared, probably they may need your help. Then we'll get back to you and see how you can probably if you can come back for some time later and probably help them with their code. I think that can be done.
Sure, we would love
Sure,
to,
sure.
and we would
Yeah,
highly
yeah.
encourage them to try it out. Yeah.
Sure, sure, sure. Thank you, Anush and Aditya. We'll close the session formally now, and I'll be sharing the resources later. Thank you.
Thank you so much, sir. Thank you so much for
Thank
this
you.
wonderful opportunity.
Thanks, thanks, thanks. Bye.
Thanks, everyone.
Bye.